All right, thanks. Okay, so obviously I'm Paul Dix, I'm CTO and co-founder of Influx. So these are monthly IOx community tech talks. For those of you who may not remember, just as a reminder, InfluxDB IOx is basically the future core of InfluxDB, and it's an open source columnar database backed by object storage. It's written in Rust, and it uses Apache Arrow extensively under the hood and as a way of having shared API and data structures with other systems. So this talk is actually, it's a lot about like internals in IOx. Some of this stuff will bleed up into how you would operate it or how you use it. But at this point, we're fairly early in the project. So we're still like getting all the internal pieces together. So it's kind of a little bit of nerdy database talk, but hopefully it'll be interesting. I'll try to keep it pretty brief, probably about 30 minutes. And then there'll be time for Q&A and stuff like that with me and Ed Robinson and Andrew Lambert, who are my co-creators with IOx. All right, so let's get into it. Before we start, I basically just wanted to have some definition of some terms. And as I go through these, if they don't make sense right away, don't worry, I'm gonna revisit them multiple times throughout the talk. So the first is called a writer ID. It's a unique U32 identifier that identifies each IOx server that's operating. There's something called the mutable buffer, which is an in-memory, writable, and queryable database. So basically it's optimized to be able to accept writes, but also be able to answer queries and stuff like that. There's another buffer called the read buffer, and this is an in-memory read-only optimized database. So the idea is it's optimized with compression and query speed and all sorts of stuff like that, but writes only happen in very large blocks. There's obviously object store. And when I refer to object store, I'm actually referring to our kind of abstraction around many different object stores. So that could be backed by S3, Azure, Google, your local disk, or memory. And later we'll add stuff, other object stores like Ceph and Minio and stuff like that. All right, just a few more terms. So data is organized, obviously there are databases within IOx, and within a database, data is organized by partitions. So partitions are user-defined areas of non-overlapping data. So very commonly, you would create, say, a partition per day or a partition per few hours. You could partition data by a measurement name or table name or by region. There are chunks. So these are blocks of data within a partition, and chunks can potentially have overlapping data, but not necessarily. So a partition is comprised of many chunks that contain its data. And then lastly, there's something called a wall segment. Wall stands for write-ahead log. And there's basically a segment of a write-ahead log, which is basically just a collection of writes, deletes, and schema modifications. They're modifications to the database. All right. So this, from a high level, this is what the lifecycle of data looks like in IOx. And I call this write, replication, and subscriptions. So there's a bunch of different things happening here. So as you can see, everything in light blue is basically synchronous. So these things happen with, you have a write that comes into the system. Those things all happen while the write request is happening, and then a response is not returned until all of the things in blue have happened. Now, one thing to note is that each of the, the second level of the tree, replicate to remote servers, wall buffer, mutable buffer, each of those things are optional. And each of those things can actually occur on a completely different server. So these things can be spread out and you don't have to use all of these things. So, and at the bottom in orange, we have the asynchronous stuff. So let me just go through the different pieces. Basically, the input format, which right now is InfluxDB line protocol, but we'll be adding other formats like JSON and stuff like that. That gets converted into flat buffers, which is basically just a really efficient binary format for having data that you want to serialize and deserialize over network. It's basically zero cost for that. You basically just copy the bytes. You can replicate to remote servers, which happens on a per partition basis. So basically you can partition your data out there so that some servers handle some data and other servers handle other data. There's the wall buffer, which I'll get into in a bit, and the mutable buffer. So mostly what I'm going to talk about, basically all of what I'm going to talk about today is that wall buffer and mutable buffer piece. So the input to flat buffers, one thing to note that's important is what happens here is, we take it either from JSON or line protocol, we convert it into this flat buffer structure, and it's all like self-describing. So it includes like measurement names and tag keys and field keys and stuff like that. But it also includes the writer ID, which is the server that received this request, and a sequence number, which is basically just an increasing U64 identifier for the individual write. And a write could be like a batch that you've written in, or it could be like a single row, a single line. So here, now we're going to dig into the wall buffer section. And it's called a wall buffer because it actually just buffers data in memory. And the whole purpose of this is to basically ship that data off to object store so they can be picked up on recovery or by other servers. So the wall buffer has a few different settings that you can have. And like I said, within a server, you can enable or disable the wall buffer. It's optional to you. So it basically has a max buffer size in bytes. So you can say like, I want the buffer to be able to take up 2 GB of memory. The buffer is split out into segments. So you specify a segment size. So for example, you could say, I want the buffer to take up 2 gigs of memory, but I want each segment to be 50 megabytes. It's optional to persist the data. You actually don't have to persist segments to object storage. You could just use the wall buffer to buffer this data in memory so that subscribers can pull that data off. And the persistence options you have are, you can persist the data once a segment is filled up to whatever that segment size is, or you can persist it based on some period of time in which the segment has been open. So you can say, once a minute, I want to make sure that whatever open segment is there is closed out and persisted to object storage. So then you can define what the behavior is when the max buffer size is reached, and segments, if you want persistence, if segments haven't been persisted in that buffer, you can choose what you want to have happen, which is you can either reject the write and return a 500. You can just drop the new writes, preferring to keep the writes in memory that you had previously written that will hopefully get persisted. Or you can just drop the unpersistent segment and keep going. So we'll go over these in a second. So the other thing about segments is they have a monotonically increasing ID, and they also, segments themselves have a writer ID assigned to them, right? Remember the diagram we had, the flat buffers, which have a writer ID, and then the wall buffer, which can actually occur on a different server. If you're buffering all those writes up that can come from different servers into a segment. When you persist the segment, it has your writer ID associated with it. So here's what the success example of using the wall buffer looks like. So say we have a 300 megabyte max for the buffer and we have 100 megabyte segments. We'd probably have smaller segments if I had only 300 megabytes to work with, but this is going to make the example easier to work through. So your writes fill up segment 1. And the way it works is basically, if a write, you write until a segment until it goes over that amount. So 100 megabytes is basically the threshold after which it will be closed out. So it's almost always going to be likely 100 megabytes plus some amount that had actually gotten written in the single write request. So when you fill up segment 1, you close out that segment, and then you return a response back. The synchronous part has happened. in the background, you attempt to persist that segment to the object store. So now new writes are coming into segment 2, which then fills up. And when it fills up, you close that segment and you again attempt to persist it in the background. And now new writes are coming into segment 3, which then fills up. You close that segment. And now this is the point at which something happens. If segment 1 is persisted, you clear it out of memory. And then, you attempt to persist segment 3 in the background. So now at this point, you have 2 segments that are in memory of 100 megabytes each, or give a little bit more. And then, the remainder that you have. So new writes basically will go into creating segment 4 or not. Basically, if segment 1 was not persisted, you can't create segment 4. So basically what'll happen now is it'll fall back to whatever the failure semantics you wanted were. If you wanted segment 1 to be dropped despite the fact that it's not persisted, then everything is going to keep going. Or you can return errors, right? So there's some interesting properties that I think are worth highlighting with the way the wall buffer is designed. So one, like I said, persistence is optional. But the other thing about persistence is that you can use replication for durability. So persistence is optional, but even if you decide to persist, there is a window of time in which writes are buffered in memory, but they haven't actually been written to the object store. So what that means is if that server goes down, you would lose those writes. So in our own setup, what we will be doing is basically replicating data to multiple servers within the request response lifecycle to ensure durability. So that if one of those servers goes down, there are other servers that have the right that will be able to persist it. And then another option that we'll have later is actually using the local disk for writing segments incrementally so that you can actually do an fsync on every individual write. But as I mentioned, our mode of operation is that actually we will not be using that local disk write-ahead log. So the other thing is that the steady state of operation for the wall buffer is that it takes up the max buffer memory minus one segment size worth of data, give or take, right? So if you say I want the wall buffer to take a gigabyte worth of memory and you have 10 megabyte segments or 50 megabyte segments, if you're operating the server, once you fill up that 1 gigabyte worth of memory, it's basically just going to keep writing in new segments and dropping off the old segments that are persisted. So it's going to continuously have that 1 gigabyte of memory taken up, which makes it nice for subscribers that may be subscribing to that data. They're just going to be able to pull it directly out of memory as opposed to going to disk or something like that. So segments can be captured, like I said, based on a schedule or a space. So you can say I want 50 megabyte segments, but or I want you to persist a segment after it's been open, say 10 seconds. So you are sure at least every 10 seconds, a segment is persisted regardless of what size it was. And what this means is you can actually have what I call serverless replication via segments in the object store. So other IOx servers will be able to pick up wall segments from other servers directly from the object store. So basically, if you have your segments persisted on a schedule, once every 10 seconds, it means you can have other IOx servers replicating that data, and they'll just have, up to a 10-second delay in replication. So I wanted to go into where the object store is, how it's organized on how the walls are organized on object store. So basically you have the writer ID. This is the path in object storage. You have the writer ID, the database name, wall, numbers, and then dot segment. So essentially segment number 1 would look like this on writer 1 for MyDB, right? So basically the first 3 digits are the millions place, the second 3 digits are the thousands place, and the last 3 digits are obviously the hundreds place. So what that means with this design is that you can only have a billion minus 2 segments within a writer. We might increase this by adding a few zeros of padding at the top level, or we could, go alphanumeric on that top level. But the choice of this 3 different tiers was basically to ensure like how long it would take to find out what the most recent segment for a database was. So basically you have one list operation against object storage to get what databases exist. And then for each individual database, you have 3 list operations to get whatever the latest segment is, right? You do a list operation on the top level of wall, then you do a list operation on whatever the last one is there. So if it's like 0, 2, 0, you do a list there. Then you do a list on the next level, and then the segment level to actually get the file name of the last segment. And actually, I think one thing that's interesting is, so the Databricks put out this paper called Delta Lake, I think it was last summer, and Andrew read it and of course encouraged me to read it, which I did. And their method of dealing with this kind of adding files on they're kind of like part of like a sequence of events that you're doing, is they actually have a separate file that they write, which is basically whatever the last file written was, right? So basically you write a segment and then you write another file that says this is the last file written. And basically that's like the well-known location. So you can always find out with one GET request what that is. I chose not to do that because the thing that's going to be ideally what's going to be happening is your server is going to be running. So it's actually not going to have to figure out what the last segment number is by doing a bunch of list requests. It's only going to have to do that on startup, which hopefully is not going to be extremely frequent. What will be far more frequent is writing a segment. So incurring the cost to write another file every time you want to write a segment, I thought would actually not be as good as essentially just doing 3 list operations versus 1 list and 1 get. 3 list operations and a get versus 1 list and 1 get for recovery. All right, so one of the biggest problems to solve is basically, if we're writing all these wall segments, when we restart, how do we know what segments of the wall, where do we start in the wall to actually recover all of the data, right? Normally in a wall, you don't replay the entire wall every time you start the server. You replay from some checkpoint in it, right? Because you had persisted everything out to there. So looking at this picture again, we're going to dive into actually the mutable buffer side of things, because the mutable buffer, and more importantly, that last part, the orange chunk 1 to object store part, is the part where we've actually snapshotted some portion of the wall into object storage in a format that's indexed and highly compressed and much cheaper to read than the write-ahead log. So here's the structure of the mutable buffer. So data is partitioned just like before. It's user configurable, will default based on time, like every 2 hours, for instance. Rows, importantly, rows can only exist within a single partition. Each partition has chunks, as I mentioned before. These chunks are used to persist blocks of data within a partition. And they're also used to ship over to the read buffer so that it can have obviously that highly compressed and optimized format. So closing a chunk and persisting it can be triggered on a number of different things. It can be triggered on size. So you can say, every time a chunk gets up to this, persist it. It can be triggered on time or combination thereof, or it can be triggered by an explicit API call that says persist this open chunk. So the important thing is that chunks might have overlapping data. They don't necessarily, They don't necessarily have to have overlapping data, but they may have overlapping data, which means that kind of has to be resolved at query time, and we have to build stuff into the system to hopefully quickly determine whether or not chunks have overlapping data. But the fact that they can have overlapping data means that chunks are how we deal with updates, deletes, and all that kind of stuff, which we'll come back to. So chunk persistence to object store, it's basically just a bunch of Parquet files. We have one Parquet file per table or measurement in InfluxDB terms. There's a metadata file, which has a bunch of data with it. So it has what tables exist, what columns those tables have and their data types, the summary statistics for those columns, the min, the max, the count. We have writer stats for the data that appears in the chunk. So for each unique writer ID, we keep track of the min and the max sequence number that we saw. And for each writer ID where we have segments associated with it, we keep track of the min and the max segment. We don't necessarily have segments. You don't necessarily have to have wall segments to get data into the mutable buffer and get it off to object storage. So then the last bit is a catalog file, which exists for the entire database. So this is a description of all the partitions that exist and what chunks exist for those partitions. And that information can be used to basically construct the paths for where those things are in object storage. So each time a chunk is persisted, a new catalog file is written. And our thinking on the chunk persistence is that this is not something that's going to happen, every couple of minutes. Like ideally, you're only going to be persisting a chunk, once an hour or more, depending on what kind of volume of data you have incoming. So yeah. So some of the interesting properties, I think, of chunks. One thing that's important is that once they're persisted, they are immutable. You can't add any more. You can't rewrite the actual chunk. Now, that being said, you can take two old chunks and combine them together into some new chunk, basically do compaction. And we'll come back to that for some pieces. I think what's also interesting is that this kind of like chunk structure enables bulk import of data. So if you have this whole mass of data that you want to import, you see that it belongs to one partition or another, you can organize it into a chunk, which then can be written directly to object storage if you're using a separate IOx server and client to do that job. It also means you can quickly bring up read replicas for historical data. You just bring it up, you point it at the chunks, they're in object storage. The other thing that is nice is that the server can boot up and it can actually choose to load only the recent chunks from object storage as opposed to loading the entire database, which obviously for time series data is super important because generally speaking, you have a very small amount of the data that is actually active for query and a huge swath of data that's basically just sitting dormant. So it's better to just keep it where it's cheap to store. So here's where chunks are located in object storage. So you have, again, the writer ID, the database name, chunks, you have the partition key, which again is user definable, and then you have a chunk ID. So for instance, writer1, mydb, we have a partition key that's basically for today. We have chunk1, and then we have a specific table, which is cpu.parquet. That's everything in the CPU measurement. So the catalog file is going to go here. Again, writer, database, catalog, and a zero padded ID dot checkpoint. So for instance, the first checkpoint file will go there. So the catalog data is interesting to dig into. So basically, like I said before, you have what partitions exist in the database. And again, the catalog data, I think I should point this out, this is the catalog data for this particular writer. each writer, it has its own like kind of namespace, its own prefix in object storage. So when it's cataloging data, it's cataloging data that it knows about and only it knows about. So, so you have partitions, you have the chunks that exist within those partitions, you have metadata about those chunks, like when it was persisted, when it was last queried. The when it was last queried is basically just going to be at the time when the catalog was written. That's not going to be updated on every single query. You have the schema, you have the summary stats, basically like you did before, and you have the writer stats. So you also have the writer stats on the chunks that were open in memory when this catalog was created, basically when the last chunk was persisted. So what you have is the minimum segment ID that had data of the open chunks. And basically we use this to figure out where in the wall, like how far back in the wall we have to go to replay from. So some interesting things about the catalog is, because of this structure, it means that you can get schema information very, very quickly, which means we can actually put schema validation at a bunch of different layers in the stack. We can do schema validation at the front door when data is parsed from the input format into flat buffers, which we want to be able to do. It also means we'll be able to have features like locking the schema for people who want to do that. It means that schema renames, like changing a table name or measurement name, changing a tag key name, or changing a field key name, are actually super cheap. Those names are actually persisted in the Parquet data that's in object storage, but to do the rename, you don't actually have to rewrite that data. You can basically just update the catalog with the information that this is being renamed to this, and then that can just be applied at query time. And then later, if you want to actually, rewrite the underlying data, you can do so by rewriting those old chunks, but obviously that'd be expensive. And then another interesting thing that we've actually never been able to do before is you can do point-in-time recovery. So you could go back to a previous checkpoint, see its data, see what it had. And like I said, because chunks are immutable, segments are immutable, you'll basically be able to, if you don't delete those old chunks and you don't delete those old segments, you'll be able to recover the data, like see what the database looked like at that point in time when that catalog was taken. And basically you can just replay the write ahead log forward from there if you want to go, forward to some point, or like not play it all the way forward, basically. So here's kind of what the restart recovery process might look like for a single database. So we get the checkpoint from the catalog. We determine the oldest wall segment to start from. And again, this is based on the information in the catalog. And then we start from that segment. We read the segments into memory as quickly as we can. We probably do that in parallel. And then we read that wall into the mutable buffer. And as we're pulling data into the mutable buffer, we only write writes that were not persisted. So remember, we had information for each chunk that's currently persisted. There could be data from this oldest segment that has actually already been persisted. We don't know based on the chunk alone, or some of the data could have been still in an open chunk in the mutable buffer. So basically we replay that and we only take the writes that were not persisted. That way we know that this new open chunk in the mutable buffer doesn't overlap with the existing data that we already have. And then another thing we can do is actually just prefetch recently queried chunks so that we'll be able to answer queries. All right, just a few more slides. So handling deletes, I just want to talk about this really quickly. This is like our plan for how we're going to deal with it. Essentially, when you do a delete, there's a tombstone, right? A delete has like a predicate that says delete from this table with these properties. There's a tombstone that will be written into the write ahead log and it'll be kept in memory. That tombstone will be applied 2 chunks at query time. So we'll apply to open chunks. We can then cache those deleted results. So basically rewrite those open chunks opportunistically in memory as queries happen on them. And the same thing, we apply it to the read buffer incrementally as chunks get read. So that should be pretty fast. So when the next chunk is persisted, we'll then mark these tombstones in the catalog. And the tombstones will be matched to each chunk that the predicate in the tombstone would apply to. So what this means is we still haven't rewritten the data, right? All the data that was deleted still actually exists in object storage in the old chunks. So what you have to do to actually remove the data from object storage is you need to compact the old chunks. Now, so like I said, say you have chunks 1 and 2, those have deletes in them, or maybe you just have chunk 1, it has deletes in it. You'd have to rewrite chunk 1 into chunk 2 or 3 or whatever. But the important thing is you can do this in the background, or you can do it on completely different servers. You don't have to do it on the same server that's actually servicing your query workloads or your write workloads. It can be offloaded to some other thing. And you can actually, if you want, have like a work queue and do all this crazy stuff. So I think that's interesting. So some of the properties of deletes, they're expensive. At least it's expensive to rewrite data. It should be fairly cheap at query time. But this is kind of a property of what we're building, right? We're building something that's designed for historical data. In my mind, if you're deleting data, I mean, obviously there are compliance reasons why you'd want to delete data. And I can talk about, there are other ways to do that. But generally speaking, you're not overwriting data, you're not rewriting data because it's a history, it's time series. So, but the other thing, as I mentioned, is you can do them all, and you can do all of this in the background on different servers, and you can compact these chunks, which is nice. It basically gives you a lot more operational flexibility into how this works than you had before. But the one nice thing is that drops are incredibly cheap. So if you have some policy where you want to age out data, that's obviously super cheap to do. You just drop those files from object storage. One of the other nice things is because data is now organized in object storage on a per measurement basis, per table, it means you can drop a single measurement very cheaply. Again, just remove those files. All right, last bit, project update, and then we can go to Q&A. So right now, Ed and Andrew are working on the mutable buffer and read buffer lifecycle. So they have a bunch of work. It's basically like this thing where it's people digging a tunnel, and Andrew's digging from one side and Ed's digging from the other side, and they're meeting in the middle. So a lot of that work is coming together right now, and the query stuff is landing basically as we speak. Now, this query stuff actually doesn't have the optimizations yet that the read buffer has, which I think is really going to be interesting once we get those in, because the read buffer, like I said, is optimized for processing queries very, very quickly. So I think my expectation is that'll land in a completely functional way within the next few weeks, and then it's just going to improve over time as the pieces get tied together better and the optimizations land. So the wall segment persistence, there's a PR for that right now. The chunk persistence should happen probably within the next few weeks, which will then lead to essentially recovery. So once we have those top 4 bullet points done, which again, I expect, like I said, to land probably within the next few weeks, that's kind of the end-to-end, an actual functioning happy path data lifecycle that IOx supports. We're going to be adding in the Aero Flight RPC. The nice folks at Integer 32 have been working with us, the Rust consultants, and they've been landing improvements to the Rust Apache Arrow project, specifically around flight, which is the RPC mechanism for transferring data. So that's going to be a great way to query the server and get back millions of records really, really quickly. So after that, we want to be able to do more optimization, but we actually want to start putting together some actual numbers about how it performs, how much memory it takes, how much space, all that kind of stuff. And I'd like to see us get builds out sometime in February. That is all I have for you today.
Well, but there's a lot of questions. So
Are there?
Go into the chat and the Q&A. I think Andrew was attempting to answer them. He thought, I'll just leave them to the team. Did you want to read them out loud and answer them? Some of them you eventually covered, but it's also good to just get these on the recording.
Do you want me to read them, Paul? And you?
No, I see it. Okay, so I'm just looking at the chat right now. Will protobuf be supported in the future? Possible, maybe. My personal preference is to support just like flat JSON objects first as the next input format. The flat buffer structure will certainly be supported, but that is for anybody who's ever worked with flat buffers before, it's kind of a complete pain to work with. If you're working in Rust, this will obviously be much easier because we have a bunch of tooling built out in that. So maybe protobuf, maybe not. Kind of depends. That honestly would be dependent on, if we do JSON, I'd essentially want to see what the perf difference is between protobuf and JSON, because essentially that's just, I assume you're asking that because you want performance. And if that's a perf optimization like gzip JSON, my guess in Rust is actually going to be quite fast. And we may not get that big of a benefit from protobuf. But again, without benchmarks, who knows? Oh, Andrew had a bunch of comments here. Okay, can read path and write path be separated, similar to Druid and Pinot for segments which are already uploaded to the object store? Yes, that's by design. Let's see, can partitions be customized like hourly and can be multi-level? So partitions aren't hierarchical, but there are rules for how you construct a partition. There's basically just a partition key, which is a string, and you can use the table name, you can use the column names, you can use a time formatted string from one of the columns, you can use regex captures from strings, you can use the actual values from the columns. So it's pretty flexible. So as long as you have like your data is organized in such a way that would kind of like that hierarchical structure would be emergent, but they're not stored in object storage hierarchically. And if you have a slash in the partition key right now, that will be escaped because we're using slashes, like we're assuming a certain directory structure within object storage. Is compaction and resorting supported for late arriving data in older partitions? Yes. I mean, by the way, a lot of this stuff is in flight. So, but for data in older partitions, you can absolutely like rewrite chunks. You can write in new chunks. You can compact stuff. And again, that's kind of by design. One of the big things, there are two big requirements that we want to hit as part of this design with respect to that. One is bulk data import, right? We wanted to be able to have like historical data where you bulk import it and you're able to bypass, the front door of like line protocol in and all this other stuff. Like ideally you'd be able to have, structure that on the client and basically just upload, big Parquet batches. And then the other is bulk data export. Which is useful, obviously, for backup situations, for replication, but also useful for, all sorts of like data science and machine learning scenarios where you want to train up a model on some big massive data. All are chunks loaded lazily based on read patterns. So in theory, they will be. They're like, none of that chunk stuff exists right now, but the goal is that IOx will be able to operate without any locally attached disk, right? So you can use object storage exclusively for your persistence layer. However, we want locally attached disk to be able to be used essentially as a cache for chunk data, right? So basically you could lazily load one chunk data from object storage into your local disk. If you have like locally attached NVMe drives, that could be really cool. But then also like, based on query patterns and stuff like that. The problem is if you're going to load chunk data from object storage based on a query pattern, depending on how big your chunks are, you could get really, really poor query, performance. So let's see, how do we control, make sure that stats don't blow off for large cardinality data sets and string columns? Cardinality doesn't really matter for the stats, right? Because we're just keeping min and max, and strings you can compare like that. So what matters is how wide your tables are. So if you have 10,000 columns, then you're going to be keeping stats for 10,000 columns. But if you have a single column that has completely unbounded cardinality, like say tracing data, for example, that won't have any impact on the stats.
Right, and even if we had more sophisticated stats later on, like a Bloom filter or something, right? That's the whole point of the Bloom filter, is not to have stats that are like a function of the size of your input data.
Yeah.
Or rather the cardinality of input data.
Post-compaction is atomic replace, so reads are not affected. So that is the point of the catalog, is that you can actually write new chunks, and those chunks can be essentially not visible until you've actually written a new catalog file. So that catalog file represents the one kind of place to do an atomic swap. And the other thing is, like I said, each catalog file gets a new name. So because the thing is, not every object store actually supports basically a put if not present. AWS doesn't, which if it did, some things would be easier, but we can't all have nice things across all cloud providers. Okay, let's see. Sorry, just going through the other ones. Is this going to be on YouTube? Absolutely. Protobuf better in terms of contract, and we can leverage registry and code generated models. Okay, this is not performance related. Interesting. We'd have to look. Yeah, did type issues in JSON. Yes, 100% for that. Yeah, so we want to be able to give people more tools on doing schema validation and that kind of stuff. So yeah, maybe that would be an interesting reason and use case for adding protobuf support. So let's see. I think there is something in, I don't know how Q&A works.
Yeah, so you have two. If you click on it, you should see it should just be like the chat will pop up.
I see the chat window, but I don't see I just see the Q&A with the flag of 2.
Okay, so Gare asked, immutable chunks, does that mean that you cannot override a value for timestamp back in time? An example, a value of 2 months back in a closed chunk.
So you write, basically how that works is you write data into a new chunk, and essentially based on the summary statistics that exist at query time, we know that this old chunk and this new chunk have potentially overlapping data. So essentially you need to resolve that overwrite at query time, which is expensive, right? So basically what you want to do is you want to minimize that kind of thing. And if you do that kind of thing, compact the data as quickly as possible. I would ask you, why are you rewriting old data?
So Gare, if you can respond to that, and I can unmute you. And then Chris Saltis was nice enough to move his question from Q&A to the chat.
I see it, yeah. Yeah, the reason why I ask why you're rewriting old data is while many of us would love to rewrite history, Yeah, so many times. That's basically what you're doing if you're rewriting old data. You're rewriting history, which is a sweet superpower. But okay, so while you're
his response. So he says rewrite. It could be time series from a calculation engine calculating back in time based on a rewrite in calc.
So it sounds to me like there might be a way of doing that sort of use case without relying on the concept of like real wall clock time, right? So you can have, because it's not just a single timestamp like in InfluxDB, you can have as many time-based columns as you like in IOx or say.
And Gary, I unmuted you, so you can, add a little bit more color if you want to.
I was going to say the other thing is you can, so in that case, what I'd say is like, it would be best to have a separate column, like if you have a calculation engine and you're like revving this calculation engine and there's different like versions of it, I would have a separate column called whatever engine version or whatever, and then use that, right? Because the truth is you don't want to actually like replace the old data. You want to write the new data. And then, if you have that engine version column, like you'll be able to actually query the previous version and the new version and overlay them, right? So you could actually write it with that same timestamp, but you actually don't want to replace the old one.
Yeah, and I think the idea is we'll support the updating of historical data, but it's not going to be fast, right? Like
Yes.
it's not going to be optimized for that case, right? So I think Paul was describing a way to get good performance out of the IOx design. If you have this case of batch uploading significant amounts of updated historical data.
Right.
So Gary, if you want to add to that, you can. In the meantime, as I mentioned, Chris moved his question from the Q&A to the chat for you, Paul.
Okay. Are there specific pros and cons that depend on the object storage you use? For example, AWS versus Google, besides performance, that is. No, not, or at least I don't think so. Or like basically what we're, for better or worse, we're designing it for lowest common denominator. So essentially like the interface for our object store abstraction in the code is the same regardless of which object store you use, right? Whether it's memory, file, Google, AWS. But as we're doing the design for how things are stored, largely AWS is driving those decisions because it has more limited functionality than the others. And it's certainly driving the decisions as far as price. Like when we're looking at like how to organize stuff in object storage and what would be the most cost-effective way to do it, S3 pricing is specifically what we're looking at.
Travis, I see that your hand's raised. If you want to ask a question, you can unmute yourself. And Chris, if you wanted to also add any more to that question that you had, you can. And if anybody else would like to ask any more questions, of course, put it in the chat or Q&A, or you can raise your hand. And I think we have just a few more minutes left, so I'm happy to unmute all lines. No? Okay, no problem. So if anybody does have any other questions, sometimes it may come up after this tech talk today. Feel free to shoot me an email and I'll forward it to Paul, Andrew, and Ed, and they'll be more than happy to answer your questions. After a quick cleanup of this video, I will post it to our YouTube channel and also the links on our community site so everyone can take another listen to it. And any last thoughts, Paul, Andrew, and Ed?
Oh, I also just wanted to add, like, if you do have questions, a great place to be is in our community Slack. We have a specific channel for IOx, and Ed, Andrew, and myself, like we're in that channel. So if you need something that's like higher bandwidth than whatever, we're happy to answer questions and also like work through design discussions and stuff like that. We're trying to do as much of this out in the open in the GitHub repo as possible. So yeah.
I will also add that Slack channel link in the email with the link to the video. Thank you, Paul. Cool. All right. Well, if that is all, then we will conclude our tech talk, and we'll be back in a month's time to see the great progress that the team has made. Thank you so much, everybody, and have a great day.
Thanks, everyone.